Okay, AP Physics C, let's quick do an introduction to projectile motion. Now, we kind of did this in class already in looking at the problems, but multi-dimensional motion in general is anytime something is moving in two dimensions. So last year we had, projectile motion, something launch at an angle, right? Or circular motion, something moving in circle, right? That's two-dimensional motion as well. Something moving in a plane, a flat plane, right? Now, circular motion, we'll come back to that. Let's not worry about that right now, but let's just talk about some of the basics of projectile motion, right? So, when we launch something from the ground, it has an initial velocity, v naught. Now, instantly, you can break that into two components, v naught y, v naught x. All right. Now those components you can determine from the angle which the projectile is launched at. So v naught x is v naught times the cos of theta. V naught y is v naught times the sine of theta. Now this is good for any multi-dimensional motion problem. You can break it into x, y components, as you can actually a circle. Something moving in a circle, you can actually break those into x and y components as well, which is a very useful thing that we'll do later on. But here we go. All right, so that's the starting thing. Now the other two things to remember basically are the fact that the AY is, if we do a normal coordinate system where up and to the right is positive, AY is negative g. No, g is not negative. G is 9.8 meters per second squared, or 9.8 newtons per kilogram. Acceleration due to gravity is negative g, and AX is 0. This is for the specific case of projectile motion. Not all multidimensional motion is technically projectile motion. Projectile motion means something flying through the air. Now, you can have projectile motion without drag or with drag, okay, as we are going to see in the lab here. In this case, this is without drag. AX is 0. If there is air drag, the trajectory of the launched particle looks much more like this, right? What happens, and we'll see this in the lab, is we have a massive amount of air drag and gravity slowing this object down on the way up. In fact, the y velocity versus time has a very big negative acceleration to start off with. In fact, almost double gravity when we did the ping pong ball in class. The initial acceleration was something like negative 20 meters per second squared. So the air drag and gravity both act to pull it back down. Now that drag force decreases as it moves up because the y velocity is decreasing. Air drag is velocity dependent. So the amount of air drag is decreasing as it moves up. The x velocity is decreasing, which contributes to this not being symmetrical left to right here horizontally, because the drag force is decreasing. The drag force is changing as in the x direction. The whole time it slows down in the x direction because there is a drag force the whole time. It's just the rate at which it slows down, the rate at which the velocity slows down in the x direction, it decreases. So actually, if I look at the velocities versus time here, velocity versus time, right? The x velocity ends up looking something like this. The y velocity ends up looking something like this, which is kind of interesting. It's they're both curved off of their normal velocity versus time graphs. In regular projectile motion, the x velocity is a constant, and the y velocity just is a nice straight line through the origin, right? So this would be when it's at its peak. The time when it's at its peak is like right where the velocity is 0. So it's kind of interesting. In the beginning, the x velocity is decreasing. It actually is curved, right? Because it's not a constant change in velocity. In the beginning of its motion, the slope of the line for the birdie was something like negative 20. In the middle, negative 20 meters per second squared. In the middle is negative 10 meters per second squared. And at the end, we saw negative 5 meters per second squared. So at the end, once the birdie starts coming back down, what happens is gravity is pulling it down, the air drag is up. So from halfway through the motion till it hits the ground, the acceleration is actually, meaning the slope of the velocity versus time graph, is actually less than gravity because that drag force is resisting gravity. Very interesting. That's why we end up with this shape, right? It really dies off. And anybody who's golfed or played baseball, watch football, you know when a ball is hit, that's what happens, you know? When a ball is hit, a nice home run ball, right? You know, here's the stand. You get that, it comes off very straight, you know? Kind of rises and then falls off. It doesn't literally rise like that, but it has a very flat trajectory. Then it kind of falls down and ends up landing very, very vertically, you know, kind of loses its energy and then falls out of the sky, so to speak. And that happens with everything. If you throw a piece of paper, if you wad up a paper ball and throw it really fast, that's what it looks like. It goes flying out a straight line, then it loses that energy, kinetic energy, and it kind of just falls. Gravity takes it down. But anyhow, that's a basic introduction to projectile motion. Again, and the basic problems, we're not going to deal with air drag quantitatively from a force perspective. We will from a functions perspective. You know, we'll have Vx equals, you know, 3t. We'll have Vy equals negative 3t squared plus 2 or something, and we have to do calculus in both directions and put it all together. So we will do that kind of thing. But initially, we just have regular projectile motion, where the acceleration in the x direction is 0, and the acceleration in the y direction is negative 9.8 meters per second squared, or negative g. And from there, it's just kind of piecing it back together. Now, one thing I talked about in class briefly when you're solving these problems is I like to use an organizational table in each direction. And those that had me for Physics 11H, you know this already. Vx, delta x and t, v initial, v naught y, vy, v average y, acceleration y, delta y, and t. So I start to use y as the displacement vector for the y direction here. So this is automatically, ay is automatically negative 9.8 meters per second squared. Often delta y is 0, right? Because it starts and lands at the same spot vertically, it's 0. Delta x is also what we call the range. The range of an object is its x displacement as it moves forward. V naught y, sometimes that's 0, right? If it's launched horizontally, it has no initial y velocity. You may remember that from last year. The final y velocity and the final x velocity, they're never 0, okay? They're not 0 for projectile motion, because as soon as it hits the ground and starts to have that force to stop it, that means the motion's over. You have a new force acting. It's not projectile motion. As soon as another force starts acting other than gravity or air drag, it's no longer simple projectile motion, all right? So watch out for that. Just a really quick crash course review, what you should know from last year about projectile motion. Hopefully this helps you a little bit, get the brain flowing so we can get rolling in class, all right? Talk to you guys later. Have a good one.